Back. Yeah, so last time we learned in the broadest terms, just with pictures, how Electroweak baryogenesis is supposed to work. And today I will try to be a little bit more quantitative. So this means, first, on a classical level, I will try to derive some Boltzmann equations that will more or less describe this picture of particles flying around and bouncing on the wall that we had last time at the blackboard. And then at some point, there's a critical moment where we have to think about how to incorporate CP violation into the system. And this then leads to the second part of this lecture, where we start to discuss this in informalism, which is this union of statistical physics and quantum field theory. But before we start, perhaps I should give a short recap of what happened last time. Okay, so the basic picture of Electroweak baryogenesis, typically we would study this in the wall frame, meaning the wall is static, but the plasma is moving towards the wall, right? And here already we see the first ingredient that we need is first order phase transition. And then the idea is that since the particles are interacting with this wall, some of them are reflected, and hopefully there is some CP violation in this reflection going on. As soon as we have some CP violating densities on this side, we can act with a Swalleron on it. Which will provide the C and also the baryon number violation. And then finally, we just have to make sure that inside the bubble, we don't generate the opposite sign of baryon asymmetry. This means we have to avoid washout. And we've seen that this leads to the requirement that phi over t is roughly larger than 1, which is coming from the fact that the Swalleron has a mass which is proportional to phi. And this basically means the Swalleron is massive enough that they're as infrequent to avoid many Swalleron processes on this side of the wall. All right, so far so good. So these are all the ingredients we in principle need, but now we would like to quantify especially this 0.2. So let's start with the general considerations of the Boltzmann equations. Okay, so what we want to study, we study the particle distribution functions in the plasma. Distribution functions in the plasma. And these are just functions which tell you how many particles of a certain species are at a certain location in space at a certain time with a certain momentum. So these are quite complicated functions that depend on 7 parameters, the momenta, the location, and the time. However, since we are doing this funny thing in the wall frame, we know that this will already simplify quite a bit in our case, because there's no time dependence. If we call this direction Z, then there's also only a Z dependence, and then there's a dependence on PZ, and again, because of symmetry, there will be a P perpendicular, which is just a combination of Px and Py. So this is in the wall frame. Okay, so now we've seen what makes the kinematics here is since there's no time dependence, the energy of the particles will not change, right? And but since the mass is changing of the particles when they enter into the broken phase, this means that the PZ momentum has to change, right? So PZ changes such that you fulfill the on-shell condition. So E squared minus PZ squared minus P perpendicular squared minus M squared is equal to 0. And since the mass in our case has a Z dependence, this will basically introduce a Z dependence in the momentum we get for a single particle. So if you have a single particle and you just follow the single particle, how it goes into the broken phase, then you can interpret this as an equation which tells you what is Pz as a function of Z as a function of these three guys which are known from the outset. Okay, so how does a general Boltzmann equation look like? Okay, so the general Boltzmann equation is just from the fact that the total time derivative of f has to be the collisions or the interactions and since we have the dependence on all these functions here, there are also implicit dependencies. So this means that d dt of f is the time derivative of f plus the velocity, the nabla of f, plus some forces. And then here the derivative with respect to the momenta. And this is again the collision terms. So here you use the fact that the force is the change of the momentum with respect to time, right? So this v is just dx over dt of a certain particle, and the force would be the dp dt. Right? All right, everybody has seen this equation before? Okay, really good.
Considering space-time, as in the CMB analysis?
No, general relativity is completely irrelevant, or gravity here.
Oh, okay.
Yeah, I mean, there's a tricky part here, and I mentioned this last time. So the time it takes from the first bubbles to show up until the whole phase changed is relatively quick compared to the Hubble time, right? So expansion is negligible. And also, since the energy scale here is electroweak, gravitational forces are not as important as electroweak or electromagnetic forces. Okay. I mean, anything coming from gravity would be suppressed with 1 over m Planck mass squared, right? And everything which shows up on the numerator would be electroweak scale here, because that's basically the physics we talk about, right? So there would be a huge suppression. I mean, you could calculate corrections from gravity and so on, but they would be completely subdominant here. Hey. Ah, what? Ah, the other way around. Okay. Sorry. Was this technical or just to look good? I'm not sure. Sorry. Okay, so let's for a moment neglect the collision terms. These are the nasty beasts that Jan spent 1 hour calculating yesterday. And in our case, they're even more complicated because we have this dependence on x and so on, while in his case, he only had a t dependence, right? For him, the system was completely homogeneous, and he had a dependence on the momenta, of course, but not on x, so this dropped out. In our case, calculating these guys will be even a bit more complicated, so ignore them for now, and just try to bring the physics that we understood here, this kinematics, somehow into a form of a Boltzmann equation. Okay? So consider again the kinematics. And now we just take this equation and we solve for Pz. So Pz is now the square root of P0 squared minus m squared minus p perp squared. Okay. And now we want to use this information that no particle numbers change. So we neglect collisions or interactions. So it's just particles flying around, right? And this will tell us if you go from one location to an adjacent location. So let's say you just move from one spot here to a spot here with the delta z. We know exactly what the distribution functions are, right? Because we just check what happens to the Vz, right? Then we go over here, and we know the number will be the same. The only thing that changed is the Pz momentum. Yeah? So just to put this into an equation, the equation that you get would be that Pz, P perp, will be f of z. And now we have a changed Pz, which in this case would be E squared minus m squared minus delta m squared, where delta m squared is just the mass change doing because of the Higgs field changing, right? So remember, all the masses are proportional to the Higgs wave. So if the Higgs wave changes, the mass changes, and because of this, the Pz changes. Okay, so now we can go to the case where delta z is really small, and then the equation we find, so this is basically dz going to 0, and we find that the z derivative of f plus the z derivative of m squared times dpz over dm squared times the pz derivative of f will be equal to 0. Okay? So the only thing I did here is I expanded in delta z, I expanded in delta m squared, and used that the z derivative of m squared is delta m squared divided by delta z. Okay. Now this almost looks like a Boltzmann equation. We just need two more things. The first one is that dpz over dm squared is minus 1 over 2 pz. Right? And then we multiply by pz, and what we get is that pz over m times dz times f minus m squared prime, or let's write this as a z derivative, over 2m pz derivative of f is equal to 0. Okay? And here we can now see that this really has the form of a Boltzmann equation. Right? So since we are in the wall frame, there is no explicit time dependence, this guy drops out. Right? The velocity is the z velocity is pz over m. This comes with a z derivative. And then we have a term which goes like dpz and has this in front, right? So we can identify now the z force as being the z derivative of m squared and a minus sign and 2m. Or in general, of course, if the mass would not just depend on z, but on all the coordinates, then the force would be just the nabla of m squared divided by 2m and the minus sign. Okay. Okay, so this means if we just start from this funny picture where the particles change pz momentum because of the mass change, then we can also bring this to a form which looks more like a classical Boltzmann equation. All right, so the first thing to check is, of course, does this make sense? And what could we check? Well, we could check equilibrium, right? Because equilibrium should be a solution to the Boltzmann equation. We know that in equilibrium, the collision terms vanish, right? So in equilibrium, also the left-hand side should vanish. But of course, in the physical case, equilibrium is only attainable if the wall is static, right? So if the wall is moving, we would expect that the wall is pushing the particles around. But if the wall is static, then we would expect that's a true equilibrium state. So equilibrium for a static wall. Okay, so in case of a static wall, the distributions equilibrium distributions. In any case, far in front of the wall, the system should be in equilibrium. Okay, so what does equilibrium mean? So let's say you have a bosonic particle, and now you go to the case where you're far in front of the wall. So how does the distribution function look like for boson? Of? So energy minus 1, no? Voila. Okay, so, and by energy, we want to write this as a function of the momentum. So the energy is evaluated at p squared plus m squared, right? And this would be the m squared far in front of the wall, which would in principle be 0, but we want to take this as a generalization of that, right? So the question is now, will this guy fulfill the Boltzmann equation or not, right? And in fact, it does. Boltzmann equations, right? So the only generalization you have to do is that now the energy squared is the p squared plus the m squared in the specific location, right? And then we can check the Boltzmann equation, but we see that this function f, is just a function of E, right? So we can write these derivatives of pz and of z as just using the chain rule as derivatives of E. So the only thing we have to check is that pz dETz is equal to m squared dz over 2 times dE dpz, okay? And this is what we want to check. And it turns out that this is exactly true, because in both cases you get just the z derivative of m squared times tpz times pz over E, okay? So the z derivative of E is the z derivative of n squared times 1 over E, right? So you get this guy. And likewise here, the pz derivative of E is pz over E, right? So you can get this expression. So this means that the Boltzmann equation is fulfilled. So collision terms are 0, and the Boltzmann equation is fulfilled. Okay, that's quite nice. Okay, so the first trivial check we just did was a success. So apparently this potentially can describe the right physics that we want to study close to the wall. So the next question is, of course, what will change if we now switch on the wall velocity? Because In this case, of course, we should find that it's not a solution. Okay, so once the wall velocity is not zero, the initial conditions or the boundary conditions far in front of the wall okay, now everybody can make an educated guess. So this is the boundary condition if the wall is static. And now we are still in the wall frame. So the wall is static, right? So the plasma is moving towards us. And now you can make a guess how this guy will change in this instance. Okay, I mean, any guess? What would you have to do in order to get from the plasma frame to the wall frame? You have to do a boost, yeah. So instead of the energy, you have to put here the boosted energy. So how would this look like? So it's gamma E minus wall velocity Pz divided by T minus 1, right? And gamma is just 1 over the square root of 1 minus the wall velocity, okay? Just a conventional Lorentz boost, okay? And now you see that this does not solve the Boltzmann equation. Okay, why not? Well, every time these guys are acting on E, they will cancel. I mean, that's basically just the calculation we did, right? But there will be one additional term when this guy acts on this one. There's additional Pz dependence here, right? So still we evaluate this at P squared plus M squared. But now we have one more additional Pz dependence here. And this also tells you that the additional term that shows up will be proportional to the wall velocity, right? So there will be kind of a perturbation coming from the fact that the wall is now pushing the particles around, and this will drive the plasma out of equilibrium, okay? So this means now we, in principle, have to calculate the collision terms and study how this effect actually works in the wall. So now the particles are driven out of equilibrium, and the collision terms will try to push them back into equilibrium, right? But this is now quite similar to what Jason presented yesterday, but I will refrain from calculating any collision terms here. Okay, so before I move on, I would like to have one or two more comments on the static case, because perhaps it's a little bit unintuitive what's really going on microscopically. Okay, so I just want to say a couple of words about the microscopic case, or microscopic picture for the static case. All right, so we've seen that here the distribution function is just the one given in terms of the energy. So this is e to the e over t minus 1. And e squared is equal to p squared plus m squared. Okay, so now imagine that you have some particles sitting here, right? And these distribution functions are now functions of the momenta, but also explicitly a function of z, because this guy contains z dependence. And let's say you would fix the momentum and now follow a particle going from here to here. Okay? The question is, does this make sense? Is the distribution function, by just using the ansatz we used, that you get here, the correct distribution function here? And in principle it is, right? So you see Pz will increase, because if you go from here to here, the mass will decrease, but the energy does not change, right? So if you have this function here, the energy on both sides will be the same, and because we have this ansatz, the number of particles will be the same, right? So everything is consistent. So now, imagine a particle going from here to here, right? It will lose Pz because the mass is increasing, but again, the function here is just a function of E, right? And since we just have this ansatz, the number of particles that you had here is the correct number of particles that you expect here. So even without any collisions, nothing is happening in the plasma. Particles are just exchanged by other particles. These guys flow over here, these guys fly over here. Everything's fine. There's equilibrium, right? There's just one tricky thing here, and that's what happens to the soft particles, okay? So if you have a soft particles, you've seen that if at some point the Pz would like to become negative, right? And the argument was, okay, if the Pz is getting, or Pz squared is getting negative, then you have the reflection. And the question is now, does this also work? The reflected particles, so you have a bunch of soft particles that are reflected, is the particle number correct or not? And what's the answer? Is it or is it not? So what would you have to check if you do this exercise? In principle, you have to go to the side and ask the question if the soft particles that fly in have the same distribution functions as the soft particles that fly out, right? So it's just the Pz, when they are reflected, just change. And as long as the number of left-moving guys is the same as the number of right-moving guys, particles just replace particles with the same particle distribution functions, right? So everything is still in equilibrium. And does this hold true? Yeah, in this case, it really holds true, right? Because Pz only enters quadratically. Again, what happens in the boosted case? Does it hold true here? No, right? So you have this term, this additional term, which is not quadratic in Pz. So if you now flip the sign of Pz, you get a different distribution functions. So what does this mean? So let's say the wall would move, and I switch off the collision terms. Do I have too many particles moving this way, or too little after a time? So forget about reflection. So initially, so the particles are sitting here, the wall is moving. Now we're in the wall frame, we switch frame, right? Are there more particles moving in this way or more particles moving in this way? They move towards the wall, right? I mean, in the wall frame towards the wall. So which means what the Boltzmann equation would enforce is that these numbers are the same. So we kind of have over densities of particles moving in this direction, okay? And this will build up particle number in front of the wall. So this is like a snowplow effect, right? So the wall is coming, it's continuously pushing more particle in front of the wall. Then the collision terms will try to equilibrate this, right? By again transferring momentum in this direction. But in essence, you have kind of a snowplow effect. So the wall is coming and pushing just a bunch of particles in front of the wall, and they accumulate in front of the wall, right? So this is the microscopic picture here. So there will be, yeah?
This doesn't mean that our ansatz is not that much correct, and in front of the wall, basically, we are not in equilibrium.
Yeah, so in front of the wall, you're also not in equilibrium. This is true, yeah.
Basically, I'm not understanding why we are saying that, okay, we are keeping this ansatz from the equilibrium, and then we are doing the boost, and then if it's not working, we are putting the collision.
Right.
Because the first thing coming to mind is
exactly. So of course, this is not a solution to the problem. I'm just saying there's a problem here, right? So in principle, what you would have to do is now the following. So let's say, call this P infinity, right? Okay.
Yes.
Then you would say the full P, full F, which is now a function of Z, PZ, and P perp, when Z goes to infinity, is F infinity, right? But in general, it will be the F infinity plus a delta F, and the delta F will be proportional to the wall velocity, okay? And now, in principle, you have to solve the full Boltzmann equation in order to figure out what delta F actually is, right?
Thank you.
Okay, but what we figured out that this guy is really non-zero, and it's proportional to the wall velocity. That's why I did this analysis. All right, so at this stage, we could, in principle, already do a couple of things if we would calculate the collision terms. So, for example, last time there was this question of the wall velocity, right? So the wall velocity doesn't care so much about CP violation. So in principle, what you could do is you could now calculate the Boltzmann equation using this ansatz, look how these distributions behave, feed this into the Higgs equation, and then study how friction works in the system, okay? And after you did all this hard work, in the end, you will understand what will be the wall velocity in a specific model, okay? But of course, for baryogenesis, we have to go one step further, and that's, of course, because of CP violation, right? So this is completely classical treatment. There's no CP violation whatsoever. And in order to get baryogenesis, we need CP violation, so we have to incorporate semi-classical or quantum corrections to this kind of Boltzmann equation, okay? Okay, so in order to study baryon asymmetry, we have to incorporate CP violation into the system. So we need a formalism that unites statistical physics because we want to have Boltzmann equations with quantum physics. And this formalism exists. It had several names. So one name it's often used is in informalism. Some call it the closed time path. And some call it Schwinger-Keldysh. Okay. So who heard one of these three words before? Good. So everybody else, this will be new, that's good, because I think it's a useful tool, and nowadays it pops up in all kind of different contexts, right? For example, people also use this when they study inflation nowadays, right? There are papers by Weinberg and the inflation community where they use the informalism to calculate cosmological perturbations after inflation. Yeah? And so this is just one setup where this is extremely useful, but this is a tool which is more and more widely used also in other fields. So it's at least, I think it's useful to be exposed to it at least once during your PhD time. Okay, so this is well, of course, it's kind of technical because I try to squeeze QFT and statistical physics into one lecture here. So of course, there's no way to do this justice, since typically a QFT lecture goes like for 2 terms, right? So to a certain extent, of course, I will assume that you know more or less how QFT works, and then just expose you to the additional ingredients that you would need in order to also inject some statistical physics into the system. Okay, and the first concept I'm going to need is a density matrix. So the first concept okay, so typically when you study collider observables, that's what you do in QFT. What you do is you start with some initial state. So you prepare some initial state, some particles. So basically, time goes to minus infinity, and then study the state at t equal to plus infinity. Okay. And one way to do this is formally the following. So let's say you have some initial state, psi, at a time t0, and typically you would send t0 to infinity, to minus infinity. And now you would like to know what is psi of t, where t goes to plus infinity. And formally, the way that you would do this is you start with your initial state, right? And then you act with a time evolution operator on it. So what's the time evolution operator in quantum field theory? Like in any quantum system? It's just the Hamiltonian, right? So formally, if you don't know anything about this, you can just write it's minus I, an integral over the time of the Hamilton operator, right? So now what you would do then typically because this is a beast, right? So imagine what the Lagrangian of the standard model is. So now we can calculate the Hamiltonian from that. And this is an operator, and it's kind of a beast, right? So now there are different ways to proceed. But the typical way in particle physics would be to use perturbation theory. Okay, so how is this done? Well, you say, okay, my full Hamiltonian, there's a one piece which I call just, these contains typically the propagators, and then there's a piece which contains the interactions, and then I would like to do an expansion in the interactions. Okay, so what do I get out if I, let's say, to leading order, of course, to leading order, this is relatively simple. So I just get in leading order just replacing the full Hamiltonian by the propagator, and then put this here. So how would this look like in next to leading order, to linear in the interaction Hamiltonian? There's one tricky bit of information here. Yes? I mean, H is an operator, right? So it's not, and also these guys are operators, so they not necessarily commute, right? So how does this look like when you expand it? Well, you have to jump through a couple of hoops, right? So the way to do it is so let's say you integrate here from t0 to t, right? You would have one exponential which integrates from t0 to t1. Then you would have the Hamiltonian at t1, and then you would have an exponential which integrates from t1 to t, right? And these guys contain the Hamiltonian. Okay, and at the end, you also have to integrate over this time t1, okay? That's how it looked like. And the same construction you would do now for higher order terms. So the second order term, there would be now 2 times t1 and t2, and so on. Okay? So what makes all this kind of messy is that you always have time ordering, right? So the order is important, but after the dust settles, you will see that time ordering is important in these kind of constructions. Okay, so how would you, in comparison now, calculate equilibrium quantities or equilibrium observables? So let's say you have an operator O, and you would like to know what is this operator O in your system if the system is in equilibrium, right? And what I give you is n. N, let's say n are energy eigenstates. With some energies. So if you act with the Hamiltonian, I don't care, the full Hamiltonian, on n, you get En times n, okay? So let's say I would give you the energy eigenstates of your system. How would you calculate in equilibrium now the expectation value of your operator? Yeah? So you want to squeeze it into states, right? But there's one ingredient missing, and that's the probability of these states. A little bit more explicit, please. So what? And the probability of these states would be what? I mean, not all states will be equally prevalent in your system, right? They are, I mean, in equilibrium, states with high energy are less probable, right? NC squared? No, what I'm talking about is just the Boltzmann factor, right? I mean, this would be your observable. So the states with a higher energy would just come with a suppression from the Boltzmann factor, right? So everybody can recognize this as something which makes halfway sense? Okay. All right, so there's a different way of stating this by introducing the density matrix. So the density matrix basically now quantifies your state, and let's say in equilibrium, this would be just n, so the sum over n, and the Boltzmann factor. Okay? And then the expectation value of O would be just the trace of your expectation value of O times rho, right? Everybody can see this? So the trace is just the sum over other states m Since these guys are orthogonal, there will be a delta mn, one sum will go away, and you end up with the same expression as before, okay? So typically, in this kind of system, even in equilibrium, if there's now a time dependence, you would be interested in how rho behaves as a function of time, right? So basically, rho, this density matrix, tells you what are the probabilities of the system to be in certain states. And this construction will also work out of equilibrium. So the upshot here is this construction also works out of equilibrium. So meaning we have to study the time dependence of rho to study the time dependence of the operator O. So basically, O of t will now be the trace of the operator O acting on rho, and I interpret rho as a function of time. So now we do the same game that we did before, right? So let's say you have given the rho 0. So this is the density matrix at some initial time t0. How will this guy now change if I develop the system forward in time? Any guesses? No, so let's say now my rho is just some probabilities. Right? It will look, in general, it will look like this, right? I have some probabilities. These are not Boltzmann anymore. This is now generalized to out of equilibrium systems. But these probabilities will change with time, right? So now I want to put this guy into here and see how this would evolve. So what's the easiest way to do this? Well, I could do the following. Instead of putting the time dependence here, I could put the time dependence in the states, right? This is by switching from Schrödinger picture to Heisenberg picture. But how does this guy evolve in time? That's the question. Yes? So you get two factors, right? You get a factor e to the minus I integral dth here, and you also get a factor here, but how does it look like on this side? Say it again? The dagger, yeah. And this will be just plus I, right? Okay. All right, so at this stage, I will switch to pictorial form and just explain how this will change your formalism. So for the collision rates, we basically integrated from minus infinity to plus infinity. And if you did perturbation theory, you had these insertions at different times, right? So there was T1, T2, T3. This is basically the interaction Hamiltonian that you get when you expand in the interactions. Now we have two of these guys. Okay, this one is the old guy. So it's basically integrating from here to here. And it's integrating from T0 to T1 or to T. So what is this guy doing? It's going backwards in time, right? Since we have a different sign here, what you're doing is exactly integrating backwards in time. And if you do the expansion with the interactions here, everything will be anti-time ordered, right? Because it's just yeah, backwards in time, right? So basically now we also have a branch where we integrate backwards in time. Okay? And now you will do the same thing as before. You do the Dyson series, so you have insertions. But now what you will find out is not everything is time ordered here, right? The guys that are on the second branch are clearly anti-time ordered because you have a different sign here, right? So what happens now if you calculate a two-point function with this guy and this guy? Well, what you find out is it doesn't matter, right? Because one guy is here, the other guy is here, right? So one is always on the right side of the other, which tells you, in this case, you have to take the combination where this is acting on the field before this guy, right? Because in the end, remember, O is a trace of O times rho, right? So basically, because of the trace, you close the loop here. Okay? So the upshot of this construction is that in this picture, you don't care about time ordering, you care about path ordering. And the way you have to order stuff depends on if this guy is on the upper branch or on the lower branch. Okay? So I know initially this is hard to swallow and to digest. So one has to think a bit about it, that this really makes sense. But that's factually the outcome. So when discussing the time evolution of rho, one has to construct a closed time path. And then consider path ordering. Rather than time ordering. Okay, so let's say in QFT, what are the basic ingredients that you would need when you, let's say, calculate a Feynman diagram? Let's say you would like to calculate in QFT just a Feynman diagram, so this kind of stuff, right? So what would be the ingredients that you need to write down what this actually means? Yeah, you need the interactions, so you have to understand what this means and what else? What are the lines? Say it again? Propagators. In technical terms, what are propagators? Say it again? Yeah, not quite. But I mean, let's say in terms of expectation values, what are propagators? They're two-point functions, right? So the first question, if we at some point want to arrive at calculating these guys, the first thing to consider is what are the two-point functions, because they don't involve the interactions in leading order, right? These are just Gaussian integrals typically. These are the most simple ingredients of the whole game. So let's now consider the two-point functions. Okay, so what we want to calculate is basically, let's say you have a scalar, phi of x and phi of y, and you would like to calculate this guy, but now not in zero temperature QFT, but in context of our out of equilibrium density matrix theory, right? So if you want to calculate this guy, in principle, you can use the same rules as before, but now you have to keep track of this path ordering. Okay, so let's imagine you calculate the two-point function, and both fields are on the upper branch. So what would you get out? So just to make it explicit here, we want to do path ordering, right? Path ordering of this two-point function. So let's say I want to do path ordering, and both of these guys are on the upper branch. So how would this look like? Well, it would look like a usual QFT, which means, what do you calculate? Calculate the time-ordered guy, right? Okay, so what would happen if both of these fields are on the second branch? What do we get? No. Now we do two-point functions, right? So we have only two times, and let's assume both of these times are on the lower branch. So we said if both times are on the upper branch, we have to do time ordering, right? So if now both times are on the lower branch, we have to do anti-time ordering, right? Just because time is flowing in the opposite direction. So both fields on the lower branch you have to use anti-time ordering. And then if one of the fields is living here and the other one is living here, then the path ordering tells you, okay, so you have to first put this field, and then you have to put this field, right? So it's kind of a trivial case. It's unordered, right? But the order is given by which one is on which branch. So for mixed, unordered. Okay, so there's now, this seems to be utterly complicated, but actually there's a way of keeping track of all the structure, and that's by just introducing an additional 2x2 structure. So to keep track of this path ordering, one can introduce an additional 2x2 structure. So what do I mean by that? Well, this guy, which is my two-point function, which is just defined as minus I, the path ordering of these two fields. I would now like to write this guy with a 2x2 structure, such that I have delta plus plus, delta plus minus, delta minus plus, and delta minus minus. And minus plus denote on which branch the field is living. Okay. Okay, so before I continue, the point of this is the following. So imagine you now calculate a two-point function, okay? And these insertions, they come with a certain time, right? So this is the interaction at y, and this would be the interaction at x, okay? And there's a time in here, so there's a time x and time y, but these guys, they live now on these branches, on the path, right? And now I just distinguish different cases. So let's say this guy is on the plus branch, and this guy is on the minus branch. Then I know that the Green's function, the propagator I have to use here, is the one which is delta plus minus. Okay? I could also consider this time to be on the minus branch, and this guy to be on the minus branch. Then I would use delta minus minus. Yeah? Okay? So it's just a bookkeeping device. If your times are on the upper branch or on the lower branch of the path, and this will tell you which is the correct two-point function you have to use for your propagator. Okay? So this 2x2 structure is just introduced such that this diagram, in the end, is just multiplication, right? Because multiplication, you see, will keep track automatically that always the plus guys are contracted with the plus guys and the minus guys with the minus guys, okay? So it's just a bookkeeping device. But in the end, if we want to make progress, of course, we have to calculate these guys, which are our propagators of the system, right? So to be explicit, the plus plus guy, which is our time-ordered guy, will be minus I times the time-ordered of phi phi. The plus minus guy, which I call delta less, will be minus I times phi of x, phi of y, phi of x. The other guy, which I call delta bigger, will be minus I the other way around. And then finally, there will be the minus minus branch, which we've seen is an anti-time ordered guy, which is just minus I times the anti-time ordered phi phi guy. Okay? Okay, so this seems horrible, because now instead of one function, we have 4 functions. But it's actually not so bad, because only 2 of these guys are independent. Okay, why do you think are these guys dependent? I mean, or how could you, let's say you start with the 2 of these guys, how could you construct one of the others? Okay, so, yeah, sorry. So let's say you would like to construct the time-ordered guy. Can you construct the time-ordered guy out of these guys? Exactly, you use the heavy side, right? So you can construct basically the time-ordered as being just the step function when the time x minus time y is positive, times the delta, I don't know, I think less, plus the opposite combination times delta bigger, right? So in principle, once you know the times, you know what the time ordering means. So out of these guys, you can construct this guy. And likewise, out of these guys, you can also construct this guy, right? So even though it looked horrible, it's only halfway horrible, because we only have 2 functions now instead of 1. Okay. So this seems quite complicated, but actually it's not as bad, because once you have this additional 2x2 structure, almost all the analysis of usual QFT will carry over. So after implementing this 2x2 structure, most of the analysis in coordinate space and I will emphasize this because we will see in the next lecture that there's also something going on there, will carry over. Okay, so what do I mean by that? So let's say you take the Schwinger-Dyson equation. So who knows what the Schwinger-Dyson equation is? Never heard? It's kind of the fundamental, well, it's the equation of motion of your quantum field theory in principle. So what's the form of it? How does it look like? No, I think you confused this with the Dyson series. Now, Schwinger-Dyson equation is basically the following. In this, so let's say you have the tune point function of your system, right? Basically looks like this. What do we do about the indices? V integral over d for v is equal to is a delta function in uv. Okay. So this basically is, so to speak, the Klein-Gordon equation of your two-point function. Okay. Klein-Gordon equation, you know. Okay. There's also a Klein-Gordon equation of the two-point function, and that's the Schwinger-Dyson equation. So this is the Klein-Gordon operator. But what I added here, I mean, if you do it to all orders, there would be a full self-energy, right? So the self-energy will pop up in this equation, and this will act on the propagator, right? And will produce a delta function, right? That's a Schwinger-Dyson equation, which is the equation of motion of your quantum field theory. Okay. Now you remember you've seen this before. Right. So, yeah. Right. So of course, this guy sometimes also have different names. Yeah. But in principle, this is the propagator, and that's yeah. Okay. So the nice thing is that in principle, everything carries over. The only difference is now that we have these plus-minus structures. So there will be an AB here, right? And an AB here, so here, let's say, call them BC. And then there will be an additional delta function, which will be AC, right? So in principle, the form of this is completely preserved. The only difference is that all these guys are now path ordered, which is indicated by this additional plus-minus structure, right? Otherwise, the equation is really completely unchanged. Okay. This is a mess. Sorry about that. There's no way of avoiding this. But just to take you home again, I will now show you how equilibrium works in this kind of system, right? Because this is a statistical system, so at some point, this has to spit out the equilibrium as we know and love it, yeah? So in the last 20 minutes of the lecture, I will try to tell you a little bit how you get the equilibrium Green's functions out of this construction and also the physical interpretation. Okay, so the first step is we want to implement boundary conditions such that we recover equilibrium. So recovering equilibrium. Okay, so at finite temperature, the density matrix is rho, and we had this before, is basically just an exponential of the minus the Hamiltonian over the temperature. And often people in this context would introduce a parameter beta, which is just the inverse temperature. So they would write it this way. Okay? And then in statistical physics, the main quantity we are interested in, so we could start from here. To calculate the partition sum. So this would be, perhaps you remember this is just that, which is the trace of the density matrix, which would be then just an integral over all the states in Q of t of this operator, right? Okay. So now we went through all this complicated work with the path ordering and blah, blah, blah. So of course it would be nice if we also could somehow formulate this guy in the language of the path, right? Can you imagine how to do this? By going from here to what we did before? So what we worked with before was basically integrals which involved minus I t integral the H operator, right? So how could you possibly go from here to here? Yeah, exactly. So this is a common trick that is used, is that finite temperature is equivalent of integrating into imaginary time. So what can... finite temperature by integrating so basically minus beta we would interpret as a time integral from 0 to, what's the sign here, minus I beta. And there would be a minus I here, right? And we want to have a minus sign, so it would be minus I beta, right? So this should work. Too many minus signs. I minus minus gives you minus, okay? So this is basically the trick we want to do. And then in principle, we can interpret this guy as a closed time path, where we now integrate in the imaginary direction. So instead of doing this, we will integrate like this, right? And this is real and this is imaginary. We will integrate in the negative imaginary direction. And then in principle, again, everything should carry over, right? So now we can, in principle, just using this small trick, we can use this formalism here, right? By just using a different path. But there's one additional piece of information, and that's this trace here. So what does it mean that you put a trace here when you integrate from here to here, and then take a trace? Yeah, of course, that's what you would do in practice. But what I now want to impose is this trace, right? So you sum over the trace. So let's say you have some field here. This is field at time t1. This is the field at time t2. And basically what you want to do is a trace. So these two guys are the same, right? So basically the trace is represented by periodic boundary conditions. Okay. Okay, or if you do it now for the two-point function, this is the so-called Kubo-Martin-Schwinger relation. And this tells you that, for example, if you take delta bigger as a function of two space-time points, u and v, and evaluate this at the time of u minus the time of v at t, this should be the same thing as delta less of u and v if you evaluate this guy at u0 minus v0 is equal to t plus I beta. Okay? That's what it means. So you basically impose, so if you have this path and you have this step, you impose that these fields, which live here, are related to these fields via periodic boundary conditions, right? And since you have this path construction, it will relate the delta bigger to the delta less in the following way, right? Okay, because everything which is less ordered here will be down here on the other branch, right? And this basically just takes care of the boundary, right? So here you are at time t, and here you are at time t plus I beta. Okay? So this is representing the trace in this construction. Okay? And this is then called the KMS relation. Okay. Okay, there's one more single ingredient that I need, and then I'm basically done. Okay, so just to make life simple, we ignore interactions. Okay, so this means that the two-point function is 0. Okay? And then you can go to this equation. So this drops out. And let's say I would like now to look at this equation where AC is less. So it's minus plus. Okay, so how does this look like? I mean, this guy in principle has an AB structure, right? But this guy does not. So this guy would come with a delta AB. So if I have an AB structure, so if this guy is minus, this guy is minus, right? Then I get this guy. And then get a minus here and a plus here, right? And this guy would be minus plus, so this is 0. So this equation would look really simple. This equation would just look like p squared, or let's say p squared minus m squared acting on delta less is equal to 0. Okay, so what does it mean for delta less if this equation is fulfilled? It's what? Yeah, it's scalar field. But this equation, what does it imply for delta less? So if you have x times f of x is equal to 0, Well, it's, if this guy is 0, then either x is 0 or f is 0, right? So how does f look like? Say it again? Right, exactly. And what does it mean for delta less than? So this guy is then proportional to a delta function, no? Okay. And this makes a lot of sense, because this just tells you that no matter what you consider, the energy is given by real particles, right? You're talking about a plasma with real particles, and in this language, it's just represented that the two-point function is a delta function, okay? In QFT, you also have virtual particles. So you have a propagator, which is also non-zero when p squared is not equal to m squared, right? And that's where all the virtuality comes from. But this is basically a classical system in statistical physics. All the particles are real, and that's why the two-point function is proportional to a delta function here, right? Okay, so what will be the equation for delta bigger? Well, for delta bigger, it's the same thing. So let's say you consider this equation for the combination plus minus, right? So this is so this guy we dropped out. So this is plus 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 minus. So we get exactly the same equation, right? So this will also be true for the delta bigger. All right, this is good news. Everything became much simpler, right? We just have two functions out of the four that we want to solve. And we took delta less and delta bigger, and now we try to come up with a normalization, right? There will be some function of the momenta in front of this delta function, and the question is, what is it? And what you have to use is the commutation relations. So does somebody remember what are the commutation relations of a scalar field? Say it again? Yeah, phi x, that's a good start. Phi y, there's something missing here? Yeah, let's skip numbers for now, and then? Okay, almost. You are almost there. Yes, I? A time derivative, really good, because that's a canonical momentum, right? But these commutation relations are called equal time correlations, right? So what you do is you have the same time here, right? So let's say these are just spatial vectors, right? You have the same time, and these are spatial vectors, right? That's how they look like. So now, if you would take the expectation value of this, right? You see that, again, these are just combinations of delta less and delta bigger, right? So basically, phi of x, phi of y is proportional to delta less, and the other combination, delta phi y, phi x, is proportional to delta bigger, okay? So now we have to do one more trick, because we want to do this in Fourier space. So basically what we are saying is that this guy, the commutator, is basically proportional to delta bigger minus delta less, okay? So let's say we are in Fourier space, so we go in Fourier space. How do we get rid of a time derivative in Fourier space? What happens to derivatives in Fourier space? Say it again? It becomes energy, right? Okay, so time derivative becomes just a P0. almost there, almost there. We just have one problem here. We have equal time, right? So how do you get equal time in Fourier space? This is a little bit tricky. So let's say you have a general function which depends on t1 minus t2, right? And now you do the Fourier transform, right? So you basically integrate over t1 minus, t1 minus, no, we want to do it the other way around, right? So we want to start in k space, right? So we have an energy function of energy, and now we want to go to coordinate space. So how would you get f of t? So something is missing here in the Fourier transform. How do you go from Fourier space to coordinate space? Yeah, but there's no exponential yet, right? So there should be e to the minus k naught t, right? Okay, so let's say now we want to evaluate this at 0 time. So what would you have to do is you would have to remove this factor, right? Okay, just put t to 0. I didn't do anything else, right? Okay, so this means, to make a long story short, and I don't want to go into details, basically the commutation relations, they imply that if you integrate over dk naught over 2 pi, don't forget the factor k naught, which is coming from the time derivative of delta less minus delta bigger minus delta less, this should be 1. Okay? And this is also true in QFT in principle. 1. That's a German 1, sorry. Okay. Pooh. This means the following. So we now figured this relationship, everything is proportional to a delta. We figured that the difference of these two guys is something once you integrate over k naught. And we figured this relationship here, which we also should transform into Fourier space. And then we have enough information to figure out what all these functions actually are. So I will not go through all the steps. Just write you the final result in the hopefully correct normalization. So what you find is the following. So delta less is minus 2 pi I. Then this delta function we find. Then there's a signum function. And then there's some so far unspecified function n, which can depend on p naught. And then we have the bigger function, which is also, so this is just a definition in some sense, right? We still have an arbitrary function here. This is a definition. And this guy will be the same thing, but there will be a 1 plus n. Okay? And this 1 is exactly this one here, right? So the difference of these guys is something, and in the correct normalization, this is basically coming out of the commutation relations. Okay, so last final ingredient, KMS relation in Fourier space. So imagine everything just depends on differences. You now go to Fourier space and you have this additional shift. You can do the same trick that I just did with t equal to 0. And what you will find in Fourier space is the following relation, that delta less, or delta bigger, is equal to delta less times an exponential of k naught times beta. Okay? So this comes just out of, so if you do the Fourier transform of these two guys, and you impose these boundary conditions, you have the shift. The shift will show up in the phase, right, of the Fourier transform, and this will spit out this factor. Okay? Can do as a homework. Okay. So if you now compare what's going on here, it will give you the following relationship. So it will tell you that 1 plus n is equal to n times exponential of k0 times beta, okay? And if you solve this, you will find that n is 1 to the 1 over e to the k0 times beta minus 1. So just Bose-Einstein. Okay? All right, so this was pretty technical. I'm aware of that. But nevertheless, I think it's instructive to have seen this at least once in your lifetime, just in order to know where to look once you want to need it. All right, so let's summarize this first part of the informalism. Okay, so we want to calculate the time evolution of the density matrix and what we've seen is what pops up is this additional path ordering which we can basically transform into this plus minus 2 by 2 structure. Then we've seen that and this is also true in general, that delta less will tell you about the state of the system. And in equilibrium, and without interactions, we recovered that particles are real. So this means that this delta less is proportional to an on-shell constraint, and that the distribution function is given by the conventional Bose-Einstein distribution function. All right. So everything seems fine. So there was a lot of work just to learn something we already knew before, that there's equilibrium and that it works. But the nice thing here is that, of course, now we can try to also do out of equilibrium, right? And the next lecture, I will tell you a little bit how to go out of equilibrium, how to get a Boltzmann equation out of the system, and then how to see the way that CPP violation really pops up in this kind of setup. Thanks. Any questions?
You beat them.
Yeah, I'm sorry about that.
No,
There's no way of avoiding
yeah,
it.
No, that was very nice. Yes.
Yeah.
Thanks for the lecture. If you use the anti-commutation relations for a fermion, you would also obtain the Fermi-Dirac in this case?
Yeah, exactly. So what changes for the fermions is a couple of things. So first of all, there is a tricky thing that basically no textbook tells you, at least not the standard one, and that's how to do a trace of a fermionic field. And when you go through the mass, you will see that instead of periodic boundary conditions, for a fermion, you need anti-periodic boundary conditions, right? And the consequence of this is that in the KMS relation, there's an additional minus sign, okay? The second thing is, if you look at the commutation relations, there are, of course, now anti-commutation relations. So instead of a 1 plus n, we will have a 1 minus n. And if you put these two ingredients together, you will see that this exactly results in the Fermi-Dirac distribution. But that the trace results in antiperiodic boundary conditions is something which is not not so obvious. And there's something which is called coherent state formalism that you have to use just to see this. And this is, for example, not explained in Peskin-Schröder, right? So Peskin-Schröder just blah, 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 and then it also has to do with this fact that in the path integral, you have to keep both fields, right? While for the boson, the integral over the momentum is Gaussian, right? So if you remember how it works, so you get rid of this guy. For the fermions, it doesn't work. And this is also related to the fact how you do coherent states and the representation of the one. I mean, you need a representation of the one, which is just the sum over blah, blah, p, blah, 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 right? And also a trace, right? And you will see that both of these things work quite differently for fermions, and this results in these antiperiodic boundary conditions. It results in the fact that you need psi and psi bar, and in a couple of other small changes.
Thank you.
So it's instructive to look at this coherent state formalism at some point if you've never seen it. I found it, when I was a student and saw it the first time, it was eye-opening to me because there were like 10 questions I had about fermions, and most of these are settled once you go through this formalism.
Okay. I think we're a bit late, so can you hold this for the discussion? Let's go for lunch, I think. Okay, let's thank Thomas again. And then we reconvene at 2, okay? Let's